I wish he'd been there. I was, going through my struggles. A great guy. Good physicist, solid scientist. I can tell you a little more, but that's probably more than I should have said already. But anyway, the upshot was that the chair did not feel that Jeff should be first author. That might cause problems with his career, his job. And so Jeff had already been thinking about that, and he was second author. I didn't feel good about being before Jeff, and so I requested being third author, and that left Neil, who had been third author, as the first author, which turns out to be a good move. Neil is in the Department of Chemistry, Professor Herret at the University of Copenhagen in Denmark, and he's been doing interviews. Europe the media seems to be more open to considering this subject seriously, and when you publish a paper, you put your reputation on the line. You say, this is what we found, and here's what we found it, and you can replicate it, and we invite you to replicate it or challenge us, whatever, that's science, okay? Then the Europeans seem to pay more attention, is my observation. The media seems to be a little more open there. For example, Niels Herret has been on TV and other interviews. In Paris, he gave a talk, for example, and so on. Oh, there's some interesting stories about this paper. If you want to ask you, Ken, about the chief editor. How many of you know about the chief editor of this journal? What did she get? Just about. Later. Let's go on to the science, son. Yeah. So here's what we observe. The same observation optically, very close in all four samples, and as you'll see, that continues. So it's an internal check on these collectors, the same observation. And frankly, if you look in the lungs of some of these survivors, I think you will find some of these same chips. Not sure how long they remain in the body, though. That's a question beyond me. If we look at higher magnification than we can do with an optical microscope, this is a scanning electron microscope. You see the red layer here. It starts to have some interesting little white dots in it. The gray layer looks quite homogeneous. This is what the gray layer looks like under analysis with an electron beam. So here's what we do. This is called X-ray energy dispersive spectroscopy. Please make a note of that. It will be on the quiz. And these peaks represent elements present. Iron, let's start with oxygen. It has just one peak. Carbon, one peak. So what happens is you're hitting the sample, so in this case the red layer, with a beam of electrons. It excites the atoms, and then they give off characteristic X-rays. And those characteristic X-rays show up at a certain energy. The scale is 1,000 electron volts. And so characteristic X-rays for oxygen are here, and it's easy to pick out the oxygen peak. The higher the peak, the more the oxygen. Okay. Carbon, there's a little bit of carbon possibly here. Iron has more than one peak shown, but it's just one isotope. It's just iron. The reason you see more than one peak, this is the K alpha peak, this is the L peak, for example, and it just has to do with details of how X-rays are produced. Okay. You can read about that if you want to Google on XEDS. Google on that. Okay, that's great. Here's the red layer, very interesting. Just thrilling to a scientist. Look at the size of the carbon peak now. Enormous. This is not just an artifact or background. It's very large. The oxygen peak is very clear. Aluminum and silicon. Let's look at this one. This has less carbon, so the others look relatively larger. Aluminum and silicon clearly there, and iron. Now, when I saw this, I'm thinking, what? Iron. I shouldn't ask him. He knows the answer. What's it? Jennifer? I'm sorry. What's your name? Oh, don't tell me your name. Just tell me what you know. Do you know what this would represent? If you've got aluminum and iron and oxygen, there's some other little stuff in it. Probably contaminants, but go ahead. This stuff, the calcium and sulfur. Okay, I'll tell you later. Okay, hold on. Aluminum, iron, oxygen. Anybody else say something?
Thermate? Gunpowder?
Thermite, gunpowder, no.
Huh.
But thermite is, the signature is aluminum, iron, and oxygen. Iron oxide and aluminum. That makes thermite, which we'll talk about. So I just wanted to see, who knew much about what we're learning, right? But you can see those essential elements are there. But then there's this pesky silicon. What's that there for? And this big peak of carbon. I was puzzled. I flat didn't know what those would be doing there. Yeah, it can't be thermite, because what's a carbon doing there? And I mean, maybe it is paint. You'd have some carbon, but what's the silicon doing there along with aluminum? I puzzled. Oh, by the way, no manganese to speak of. The nominal composition of A36 steel, as in the towers, has about 1%, 0.8 to 1.2% manganese, Mn. I don't see a manganese peak. It would be right there, not there. See, I don't see it. Of course, these are pretty small, these two. You shouldn't see it if it were there. And we've looked at lots of these red chips now. By the way, what Jeff Farrar did is he broke open the red chip. See, the dust from the World Trade Center collapse is just full of elements. You've got titanium, you've got calcium, because of the wallboard. And you see some calcium. This could be a little bit of contamination. Even though he broke open a fresh surface, that dust gets around. He broke it open in air, you see, for example. You've got, I don't know, chromium, all sorts of, just lots of elements. But when you crack open to get a fresh surface, you see the dominant elements here, quite clean. Here you can pick them out easily. Carbon, oxygen, aluminum, silicon, and iron. Okay? No zinc. Please notice that. No zinc. And why is that important? I'll show you. No manganese. This is not from the steel of the building somehow, combining with aluminum in the building, because then you would have manganese, you see. Yeah, manganese from the steel. It's not there. No zinc, and that is important. Here's why. I'll try to go through this a little quickly. This is from Appendix D of a NIST report, the NIST report on the tower's demise. And if you look at the composition of the primer paint, that was one of our considerations. You see that there is zinc, yellow, included a lot of it. What's that, 20% approximately. So a lot of zinc, and in the pigment there is also zinc, magnesium, and so on. This is the Tenebec paint used in the World Trade Center 7, as reported by NIST. This is just fact, okay. But where's the zinc? There's lots of zinc in the primer paint. There's no zinc in this red material. Huh? Even Frank Greening agreed, this does not look like paint, folks. Okay. You know Frank. Blessings to you, Frank. He's interesting. Mark Basil in New Hampshire, working independently, completely independent sample. He didn't clean up the surface, obviously. He's got a little bit of titanium, but no zinc. But he's got the other peaks that we see. You see, along with some contamination, iron, silicon, aluminum, and carbon. Okay, and then, like I say, if you clean it up, you should be able to get rid of the calcium, titanium, chromium, and so on. That's his work, and he's getting ready to publish. Remember, if you repeat our experiments, you want to get a clean sample. You can clean it in other ways, but Jeff cracked it open to get a fresh surface. Good way to do it. Soaking the chip in a strong paint solvent known as methyl ethyl ketone, MEK, did not dissolve the chip. Ha! No zinc, and now this. It's not looking like paint, folks. And that's why I soaked the chip initially, several finally in the methyl ethyl ketone was to see if they would dissolve. And then I soaked paint samples as well, and they did show dissolution, dissolving, and very much limited.